In our previous films, separation of flow from a boundary was treated as a purely geometric effect. A plate or orifice diaphragm, for example, is usually too thin for the flow to follow without an impossibly low pressure at the edge. Separation simply reduces the curvature of the limiting streamline till a physically possible pressure field is realized. In general, however, separation requires not only an adverse pressure gradient, as in any region of deceleration, but also a zone of already retarded flow, as is produced by shear in the boundary layer. Here, the central streamlines do not separate as the pressure rises toward the point of stagnation, because the flow between them is not otherwise retarded. But the fluid in contact with the splitter plate is already at rest and cannot be further decelerated, so that separation must take place if the flow is to continue. As the boundary layer develops around any body of appreciable curvature, the point of separation rapidly moves forward from the zone of maximum pressure rise at the rear to the zone where deceleration first occurs. As a matter of fact, no change in boundary alignment is really necessary, just so long as there is a shear zone of low velocity and an adverse pressure gradient, such as prevails beneath the front of this undulous surge, moving slowly against the flow. Separation leads to three important occurrences. First, it changes the anticipated flow pattern. For instance, this channel expansion obviously does not cause the flow itself to expand as rapidly as desired. Secondly, it produces boundary drag, thereby expending energy through the generation of eddies, which rapidly transform to turbulence. Finally, it can lead to oscillation of the flow, with a corresponding pressure fluctuation, boundary vibration, noise generation, and perhaps even structural damage. Though separation is very essential in the operation of parachutes and baffles, it should in general be avoided by the control of the boundary layer or the pressure gradient, or of both together. If the boundary moves with the flow, for example, the retardation by shear is offset, and separation obviously is prevented. Much the same elimination of separation is realized if, as is now beginning to occur, fluid is discharged tangentially into the boundary layer region through boundary slots. Even better results will next be seen to obtain as the boundary layer fluid is sucked into the slots as rapidly as it is retarded. A change in the pressure field as a whole is provided by the introduction of guide vanes. These can be made to conform to the original boundary and thus increase the relative radius of curvature locally, or else the whole structure can be redesigned accordingly, as in the case of this miter bend. The flow is obviously much worse without the vanes, but much more efficient once vanes have been installed. A type of Euler number that indicates the effect of separation is known as the drag coefficient. The longitudinal force exerted by the flow per unit projected area in its ratio to the stagnation pressure. For extreme degrees of separation, as must occur at the edges of this disk, measurement of the pressure distribution at the numbered piezometers on the front and rear faces will show the cause of the drag. As air now begins to flow from left to right, the front of the disk becomes subject to positive pressure and the rear to appreciable suction. The integral of the pressure distribution will yield the same force as that measured on such an air tunnel dynamometer. The high drag of the yellow disk can be reduced appreciably by adding a rounded front, which minimizes the curvature of the separation surface and thus somewhat alleviates the pressure reduction at the rear. separation is almost completely eliminated by adding a well-faired tailpiece to reduce the adverse pressure gradient. Since there can be no resistance to steady irrotational flow around a body without separation, practically the only resistance now is that of shear within the boundary layer. Under optimum conditions, the process called streamlining can reduce the drag some 95%. Since the resisting force varies with the projected area of a body, as well as with its shape, at the same velocity, this streamlined form would then produce no more resistance than a disk of less than a quarter its diameter. A sphere is intermediate between poor streamlining and good streamlining. As can be seen from the distribution of pressure measured at the numbered piezometers, when flow takes place from left to right, the low pressure at the rear, compared with the high pressure at the front, indicates that separation still occurs. As is shown by injecting smoke into the wake, the line of separation is even ahead of the midsection. Making the boundary layer turbulent prematurely by a tripwire tends to reduce the separation tendency, as is evident from the shift of the separation point to the rear of the midsection. Compared with a body producing two-dimensional flow, like this long plate, a more nearly axisymmetric body, like a square, has a much higher wake pressure and hence a much lower drag per unit area. The drag coefficient of a square plate, therefore, is increased by cutting it into more nearly two-dimensional strips and slightly separating them. A body that is in the wake of another, being in a zone of reduced velocity, experiences a great reduction in drag, as any cyclist who has coasted along behind a truck is well aware. These elementary principles also apply to more complicated structures, such as buildings. Roofs should not be designed for only positive loading, since in high winds they are more likely to be lifted by suction due to separation than they are to be blown in. Chimneys, obviously, should not terminate within zones of separation, or the smoke will fill the region behind them. This is seen to be the case almost regardless of the direction from which the wind comes. Probably the most unstreamlined body is a parachute, but obviously even this can be designed for maneuverability. Moreover, even the human body in free fall can control its turning moment about 3 different axes, as this skydiver clearly shows. The mathematical concept of circulation, introduced in connection with vorticity in our second film, is also useful in analyzing the cross thrust that is exerted upon certain bodies in relative motion. The circulation gamma is defined as the line integral of the tangential component of the velocity completely around a closed curve. It's thus a measure of the tendency of the fluid to circulate around the curve, either in the one direction or in the other. The circular streamlines of an irrotational vortex are all lines of constant circulation, for the velocity varies inversely and the circumference directly with the radius. Now, if the velocity field of such a vortex is superposed upon the velocity field of irrotational flow around a body, say a circular cylinder, the velocity on the one side will be augmented and on the other side diminished in proportion to the relative strength of the circulation, and the flow pattern will change accordingly. Where the velocity is increased, the pressure will be reduced, and vice versa, so that a side thrust will be exerted upon the cylinder. Such circulation can be produced in actuality by boundary layer shear around a rotating body. This is illustrated quite graphically by rolling a light paper cylinder down a miniature ski jump. Because of the rotation of the cylinder, as it leaves the jump, the cross thrust will cause it to deviate quite markedly from its normal parabolic trajectory. The same effect causes the deflection of a spinning baseball or a spinning ping pong ball from its normal course. If a cylinder is not rotating, however, oscillation of the flow pattern will cause the circulation to vary first in one direction and then in the other, with the result that there is a rapid oscillation in the cross thrust. This explains the tendency for telephone wires to sing in a high wind, or it explains the whistling sound that is given off by this rod as it's swung rapidly through the air. Observation of the flow pattern behind such a cylinder will reveal the alternate shedding of vortices either side of the center line, the circulation around each vortex being just the opposite of the momentary circulation around the cylinder producing the side thrust.